Basically, today we're going to cover like 4 topics in the lecture notes. Like first, we're going to give a definition. We're going to talk about discrete random variable. We're going to give a definition of it, and then we're going to talk about the expected value of a function involving the random variable, like in this form. Then later on, we're going to talk about a shortcut to get the variance. It's different from the formula that we learned before. And the last topic is about linear combination of random variables. We're going to discuss how to get the expected value and variance standard deviation of maybe in this form expected value of 3x minus 2y, and xy here are just random variables. First, we're going to talk about discrete random variable, the first topic. So typically we use a capital letter X to denote a random variable. So as we learn, do you know we have 2 types of random variables? One is continuous, another one is discrete. All the things we learned before, we use the Z distribution, the T distribution to get the probability of something. All the things that we learn, we use is continuous random variable. We could take any values in a specific interval. But in this case, for discrete random variable, from the word, intuitively, it can only take countable values. Which means it can only take specific values here. For example, countable numbers of values x1 to xn. And there's also a formal definition in your lecture notes that the range space of X consists of a countable number of values. It might seem a little bit abstract. Let me give you an example for that. So this is an example for a discrete random variable. For example, here, if the random variable here is the number of phone calls a receptionist will receive in an hour. Why this one is a discrete random variable here? Because for the receptionist could receive 4 phone calls or 5 phone calls, integer number of phone calls. But it cannot take any value, he cannot receive 3.5 phone calls, right? So which means that at that point it's kind of undefined for 3.5. So that's why it can only take countable numbers of values for a discrete random variable. Okay, so then we're going to talk about for kind of the same pattern. We give a variable, and then we're going to talk about the probabilities, expectations, and something like that. So here, it might be clear. So for each values, the discrete random variable could take, there's a probability associated with it. So for example, x1, x2, blah, blah, to xn are the values that this random variable could take. And the probability corresponding to that value is px1, px2, blah, 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 to pxn here. And obviously, there are kind of 2 properties, or you could say 2 conditions for this. This probability here, you could see that, of course, for each value, the its probability should be bigger or equal to 0. Probability cannot take a negative number, right? And also, it's very similar with the thing we learned before. The summation of this bunch of probabilities should be 1 here. And in this case, we call the px is the probability mass function. There's a minor difference from the did you remember a probability density function? Did Baku talk about that or no? Yeah. Yeah. So it's different from for continuous random variable, it's called probability density function. For here, we call it probability mass function for discrete random variable. Are you guys clear? Yeah. So, okay. So, for like, there's an example in the lecture notes. It's like toss a fire die. I just use the example, like the same example in here. So if you let x denote the number, x here denote the number that you will get when you toss a die here. So for x, so the possible values for this random variable is just 1 to 6, right? 1, 2, 3, 4, 5, 6. And the probability associated with it just 1/6 for each value because it's fire die. Like, so the probability that you could get 1 is 1/6. You could get 2 is also 1/6. The same to 1/6 here. Here we're gonna like visualize what the probability mass function would look like. So for each value, so this x-axis denote the the values that this random variable could take. In this case, is 1, 2, 3, 4, 5. This one's 6. And it's this kind of y-axis. It denotes for the probability of that, like the probability of that value. So when x is equal to 1, so the probability associated with it is 1/6. Suppose this point is 1/6. We got 1 point here. And for 2, the probability of it is also 1/6. And blah, and we could get like 6 dots in this graph. So that's why it's like discrete. I mean, it's kind of, it's not really continuous. You know, like we learn like probability, like density function. It might like this one. It's really continuous, like a line here. In this case, we have just 6 dots here. So pay attention to that. There's no value between 1 and 2. Here, there's no value here. For this point here, no value. Yeah, R1 follows. Yeah, this is like the thing like about discrete random variable. So if you have any questions, just stop me, raise your hand. Then like after we know the probability, like we're gonna talk about like the expectation, right? We could like, so the expectation like in here is mu, like they are just kind of equivalent. They're like 3 things equivalent to each other. We call expectation, mu, like mean or expected value. For discrete random variable, this is the formula for the expectation of the discrete random variable here. So basically it's talk about like, you take the summation of the product between the value and the probability associated with it. This is the value, this is the probability. You take the product of them and then do a summation. Here's a quick example. When you, like, once we know the formula, it's just very easy, right? You just plug the number inside. So there are only 2 values x could take, like -40 and +2 here. So for -40, the probability associated with it is 7 over 8, right? Just times 7 over 8. The second value is 2, and the probability of it is 1/8. Could, like, anyone give me the answer for that? I don't know. I need to check. I didn't get it. Oh, it's not, okay. This is the way to get the number. I mean, just, okay, you can plug the number in the, like, do it in a calculator or something. Yeah. Did you get a number? Eight what?
Negative 34.4.
Negative 34.75. Yeah, it's kind of makes sense. You know, for the negative number, there are the 7/8 probability. Like the majority of this distribution is negative number. So, like the minus 40 is much bigger than the 2. So that's why we got like a negative expectation. So also we could check, I did before, like the like here, like the summation of the probability is just 7/8 plus 1/8 is 1. We could get like the summation of the probability is 1, and we can also see like the probability is like greater or equal to 0, greater than 0. So in this case, we call like this is a valid probability mass function. Kind of use the conditions we talked about before. Like for each value, the probability should be greater or equal to 0, and the summation of all the probabilities should be 1. Like, just review for the probability mass function here. Then, we're going to do the examples in the lecture notes. It's about the, I think it's on the page 2, like X be the number of prisoners. So here's the data. And the question is asking for like the expected, like the mu, the expected number of repeat of enders. So here, like, we just did the exact same thing we did before. So we took the, this would be a coincidence. We take the product of the possible values times the probability associated with it. So we could get it like have 5 possible values here. So you can the expected value just 0 times 0.237 plus 1 times 0.369 plus 2 times and all the way down to 5. 5 times 0.001. Yeah. Then we could get the answer is 1.25. So like this means like the expected number of repeat of enders out of 5 is 1.25. I mean, like I think Baku like in her slides like gave it like a different interpretation, but almost like the same. It means like 25% of this of enders will repeat. Will become like a repeat of out of 5. So like means like, how do you say, 25% of the prisoners will become like a repeat of enders. So how could get the 25%? it just use the expected value here. Divided by 5 is the total possible, it's the number of possible prisoners in this question. It got 0.25, which means that 25% of the prisoners will become a repeat offenders in this case. Okay, so what's up?
Why are you dividing by 5?
It's not about this problem. I mean, for this problem, it's just compute the expected value, expected number of something. You just stop here when you get the 1.25. But because like in Baku's notes, he gave like a 25%, like in her notes, it's kind of like a expansion of this problem, I think. I mean, if for this problem, just 1.25, and then it's done. And then like in her notes, I mean, he gave like 24% kind of interpretation, like just, it's not the answer for this problem.
Right.
But I think.
I'm saying there's 6 values, so why are you dividing by 5 instead of 6?
Oh, hold on. It's like out of 5.
0 to 5, so it should be 6. Right?
Yes, but hold on. So this is the expected number of repeat offenders out of 5. And it's useful. You should just, okay, hold on. How to explain this? Okay, hold on. Out of 5, because the X is number of prisoners out of 5. Honestly,
If the problem says 5, but if you include 0, it should be 6.
but number of expected value, hold on. Yuanchen, do you know how to explain this one?
I think the 0 doesn't count.
Yeah, it's like doesn't count, but I don't know how to give like a
0 is 0.
very perfect explanation, right?
It's 0 prisoners, so they don't include it.
Okay. Meaning, okay.
Okay, hold on a second. We'll go back to this part later on because it's. I can't really think like a perfect or like explanation of it now. So we'll go back to this one later on, right? Okay? Okay. Thank you for pointing this out. Thanks. It's like, okay. So then it's another topic. I mean, expectation of a function of a random variable. Here, like, this is the expectation for a random variable, and then we define a function, h. H, like, has some relationship with x. That's why we could, the function is have relationship with x. Yeah, so hold on a second. Let me give you another one. Okay. So we want to get the, hold on, let me do another one. Oh, okay. Suppose there's another random variable called y, and this random variable has some relationship with x. So we could use a function to describe this kind of relationship. So that's why, like, we talk about like this topic here. It might be useful. So the expectation of a function of a random variable here. This is a function, and it's basically kind of the same thing. here we use xi, because the thing in the parentheses is x, right? It's xi times the probability of it. So, but in this case, here's a function here. So the expected value is just at each value xi. So the function will have a value corresponding to each xi here. So we use the value of the function is hxi times the probability associated with it. It might, okay, it might seem like fancy. I mean, but then like when we go to the example, it will become like clear. Like when I learned this stuff, I didn't really learn the function thing. Like we just go straight to that. Like, for example, here, just like the same example we did before is toast the fire die. So the possible value is 1 to 6 and probability just 1/6 for each value. So in this case, we're going to calculate the expected value for x squared. So for this type of problem, like now we could, for x squared, of course we need to get the value of x squared, right? So we could do is like, we make another column for x squared, and we calculate each value. So for xi squared is just 1, right? x2 squared is just 4. x3 squared here is 9, 16, 25, 36. Now, we got the expected value of it. You know, although the values are different, I mean xi and xi squared are different, but the probability associated with it, like its probability is the same, remain the same, right? For each value of xi squared here, the probability is probably just 1/6. So we did the same thing before. We take the summation of xi squared times the probability of xi squared here. In this case, we have 6 values. The first one is 1. 1 times 1/6 plus 4 times 1/6 down to 36 times 1/6. And then we will get the value here. So I would say like if for this type of problem, is one say like compute the expected value of a function. First thing like you need to do is get the value of the function, like we did here. The function here is x squared. So we need to get the value of x squared for each case, right? 1, 4, 9, 16, 25, 36. We'll get the value of it, and the probabilities like kind of remain the same for each case is 1/6. And then do the same thing here. Are you clear? Okay, so another example. What's the value? Okay, let me check the answer. The final answer here is just, yeah, it's 91/6 for this part. And then there's a second part, is compute the expected value of 3x squared. There are like 2 ways to solve this problem. Of course, you could do the same thing. We compute the value of the function for each case. In this case, we just use 3 times 1 here, 3 times 4, 3 times 9 is 27, and this gives 48, this gives 75, 108. This is the value of the function here. And we could do the same thing. We could 3, just summation of 3xi squared times the probability of 3xi squared. We just did the same thing. We could use 3 times 1/6 plus 12 times 1/6, down, blah, blah, down to 108 times 1/6. Then you could get a value here. I think is get a number like this. This is a way to solve this problem. You just compute the value of the function. But you know that it like a little bit complicated. You need to like 3 times the 36. I mean, it's a large number. Like you cannot do it. Sometimes we need a calculator or something to solve it. Like, so like this 3 is okay. But what if I take like expected value of like 31x squared? Do you want to get the value for each function? You don't want to do that, right? It just lots of computation. There's a shortcut for this one. Hold on. Just ignore this one. There's a shortcut for this problem. We could see from the number here, this number is only 3 times 91/6, right? 3 times 91 gives like 273. It's 3 times the number here. And we could see this number is exactly same number like here, the expected value of x squared. This 91/6. And we could get something. So like so this expected value, 3x squared, is just 3 times the expected value of x squared. So like when you say a function, for example, like just a random thing. Suppose this is not related with this problem. Suppose I give it just a random expected value of a random variable. The expected value of a random variable, suppose this one is 6. What if we want to calculate the expected value of 6x? You just factor out the 6 outside times ex is give you 36. Are you clear at this step? Or no? Clear? So it means like there is a constant coefficient in front of a function. You could just pull out this coefficient outside the expected value and then take the product of them. And that's the point like I want to address here. We're going to talk about this point later, but just remember here this, yeah. Then like we're going to do another quick example, like the example here. This is a probability mass function. There are only 2 values the random variable could take, -1 and 3. The probability for -1 is 1/3. The probability of 3 is 2/3 here. Suppose I want to get the expected value of x squared. So the same thing, we need to get the value of the function first. Make another column, as x squared. So we could get 1 here, -1 squared, just 1. 3 squared is 9. After we get the value of the function, we could get the expected value here. Basically, we just take the value here, times the probability of it is 1/3 plus 9 times 2/3. And then we're done. This will give a final answer is 6/1/3 here. Yeah, you could check the answer later on. This is the approach. We're gonna solve this type of problem. Yeah. Okay, this is another like function here. Now, right now we just practice like the formula for the expected value for a function, right? Just the same thing we did before. This function here is x minus 1. Also for this case, there are two ways to solve this problem. One, you could just get the value of the functions. Another one, there's a shortcut for this one. So first we just use the traditional way. We get the value of the function here. We could get this case, x minus 1. For each x values, x minus 1 is just 0, 1, 2, 3, 4, 5, right? And when we get the expected value, we use this summation of xi minus 1 times p, xi minus 1. We could get 0 times 1, 6, plus 1 times 1, 6, blah, blah, times 2, 5, times 1, 6. And the number is 2.5. This is the way we could do this problem, but still kind of involved. And then like there's a formula for this case. Expected value of x minus 1. You could see here's 2.5. Like the previous expected value of ex we got is 3.5, right? Did you remember? Or I did give the number for that. So expected value of total Faraday. Did I give the final answer for that case? Or no? Like the first, I may forgot to give you the number for that. Yeah, I didn't give you. Okay. So ex minus 1, I just gave it to you. So probability, the expected value of total Faraday, the number we got is just 3.5. You could get this number when you take the product of xi times pxi and then do the summation. You will get this number for ex. So now we could see this. So for ex minus 1, we just from looking the number here, we could get, this is just nothing but ex minus 1 here, right? So this like makes our life easier. Once you get ex, you could directly get ex minus 1. Obviously, like you could also get the expected value ex minus 2. What's the expected value of like x minus 2 here? What?
1.5?
Yeah, 1.5. So it's just ex minus 2 here. This kind of makes our life easier. I mean, what if I want like the expected value of 2x minus 3 here? Do you know how to get this one? Do you have any clue about this?
2 times x.
Yeah, 2 times.
No, 3.5. Yeah, minus 3.
Right? Did you get the point here, everyone?
Yeah.
And we will go back to this one later. Like we're gonna like give like a bunch of formulas about this one. So just 2 times 3.5 minus 3. Really easy, right? Then, okay. That's all the thing like about the expected value of a function. Now we're gonna give like we calculate the way that we calculate variance with something. Did you remember when we calculate variance with something like this one? Right? This should be in the here. With a this is the old way we get the variance. Now we introduce like kind of a nicer way or something is to calculate the variance. There's some derivation about this to get how to get the variance. Basically, we use some rules in the, in her notes she didn't really talk about too much. Basically, you could derive this formula from the traditional one, the old one that we learned before. When you manipulate with the formula, like a little bit complicated. When you use the expected value of a function, we could derive this. We could get something like this. Maybe just remember this one. The derivation of this formula is not important for this class. This is a new way to get the variance. Then let's do an example of it. This example should be on your lecture notes on page 3. Is compute the standard deviation of x. Okay. If we want to get the standard deviation, we need to get the variance. According to this formula, if we want to get the variance, we need to know the mu here is just expected value. We need to know the expected value of this random variable, and also we need to know the expected value of the random variable square here, the ex square. So first, we get the expectation of this random variable, just super easy. I don't write the formula down, just 0 times 0.05 plus 1 times 0.1 plus 2 times 0.2 blah, blah, down to 5 times 0.1 here. I got 2.8. Okay, did I do this before? Yeah, I got 2.8. Then we need to get ex squared. Why? Because if one get this the standard deviation, we need to get the variance. To get the variance, we need to use the formula here. So then, for ex squared, it's just we just square each values and then use the same probability. So the first case, 0 squared is just 0 times the same probability, 0.05 plus, remember this square here, we use 1 square here. 1 square is just 1, right? Times the probability of it, and then plus 2 squared times 0.2. We do the same thing down to 5, so it's 5 squared times 0.1. So the final answer here is just 9.4. Okay. Basically, we got like we build the foundation. It's like very simple things left. For the variance, it's just ex squared minus ex squared. The ex here is the same as mu. They are equivalent. As we talked about before, like in previous one, we talked about like there are several equivalent like terms, like mean, expected values. They are the same. Here is the mu is the same like expected value of x. Then we just plug the number in. 9.4 minus. Pay attention to this. Sometimes like people just forget to. Here is ex squared, the expected value, the square of the expected value. You cannot minus 2.8. This is wrong. You need to square it. Sometimes people forget to do this. And the final answer is 1.56. And so because when get the standard deviation. The standard deviation here, like in the notes, like she introduced a new symbol. It's sigma x to denote the standard deviation here. I think she introduced a new symbol here. You didn't use sigma before, right, in her class? You used that? Sigma? Yeah. Okay, maybe, okay. I forgot, yeah. So for sigma x, you just take the square root of the variance here, square root 1.56, and the final answers is just 1.249. You could just write the answer down and then check. Oh, there's the solution in the lecture notes. This is the shortcut for the variance. Yeah. Let's go to the last topic. It's about like a linear combination of random variables here. The first case, the formula I gave here, yeah. There are like 4 basic things you have to remember. The expected value of a constant is just the constant itself. Is it clear? Or do you need an explanation for this one? Clear, right? And then what I did here. This should be A here. Yeah. So the expected value of around coefficient times x it just, so here is A, is a coefficient here. It's just A times expectation of x. We point out this, we mentioned that before, right? We did like similar, we did like maybe 2 examples in previous. So A times the expected value of A times x, you just pull the A out. Expectation A times EX. A times the expectation of x here. So for sigma, the standard deviation of a constant value is just 0. It means constant. I mean, it does not change, so there's no variation. That's if no variation, so the standard deviation is just 0. Quite intuitive, this one. And also like the variance of a constant is 0 as well. Variance, because no variance, if constant, just no variation, 0, 0 in these 2 cases. So in other words, the variance of AX here. This is a little bit like we didn't like give an example before. This one is just A squared times Vx. Just remember this one. I didn't give any example regarding this one, like a concrete example to demonstrate this, but just remember this one. Ex. So what about like the variance of minus 2x here? Do you know the answer for this one? This is the coefficient here. Yeah,
Minus 2 squared.
Yeah, minus 2 squared. Remember this case, you need to take the square of the value here. So just 4 variance x. Yes. And then like we talk about sigma, right? So for sigma AX, it's just the square root of variance AX, and then square root of A squared Vx. This gives you VA square root Vx, and then A sigma X. Is it a little bit complicated? So for sigma AX, you just factor out the A here, and the sigma, A times sigma X is equal to sigma AX here. So remember that for expected value, but you just put the coefficient outside the parenthesis. It's A times EX. For sigma, the same way, you put this A out. You kind of factor it out, or like just put the A outside. It's A times sigma X. Only for variance, you need to take the square. Are you guys clear? Oh, it's a little bit messy. Sorry. And then it goes to a linear combination of random variables. In this previous case, we only talk about one random variable x. Then we're going to talk about like the linear combination of a random variable. Suppose L is a random variable which is equal to A plus, this is not, oh sorry, this is just an example to demonstrate that. Okay, ignore my previous statements. Okay, just do an example here. So the x, L here is a random variable, is A plus Bx. So A and B here are just coefficients or constant. You could think about that. So we just do this. So the expectation of L is just expectation of A plus Bx. So, I mean, is it clear to anyone, the answer? It just, we could separate this. We get E A plus E B X. Because A is a constant here, the expected value of A, this is a constant. A, the only random variable here is L and X. And A and B are just constant. We do this thing. If the expected value of a constant is just the constant itself, plus here we just put the B outside. B times EX. And the EX here, we could write it as mu, because we say they're equivalent, times mu. And then we're done for this example here. The second is the variance of A plus Bx. Okay. We do the same thing. We could separate them out. We A plus the variance of A plus the variance of Bx. As we learned before, the variance of a constant is just 0. And then plus, this is B here. For variance, if there's a coefficient, like Bx, B is a coefficient for this function, remember that we need to take, if we want to put the B outside the parenthesis, we need to take the square of it. So in this case, we got B squared times variance of X. I guess clear? Okay, so next example. It's not really example here. Oh, this is just general formula. Okay, never mind. It's like. So for this case, suppose W is a random variable. The random variable is AX plus BY. A and B are constant here. X and Y are random variable here. If I got the expected value of W, we do AX plus BY. We separate into two expected values, it's EAX plus EBY. Yeah, we could separate them for expectation. There's no like constraints. For xy, it could be independent, it could be dependent. For expected value, we could just separate them out. But it's a different story for variance. So here, do the same thing. Pull the A out, plus B times EY, down. It's very straightforward, right? Nothing fancy. Yeah. 5, 6. Okay, for variance, it's a little bit different from expected value here. For expected the value is just, we could just separate them out, right? This is for the expected value of W. We could separate out into two expected values, like one expected value is about like one variable, another one is corresponding to another variable here. But in this case, for variance, like intuitively, you might think, okay, just variance of AX plus variance of BY here. You think, okay, we may just follow the same way like for expected value here. Like in our class, yes, we could, let me just do this. But there's a constraint for this case. If we want to do this, separate the variance into two parts here, the constraint is X, Y have to be independent. This is very important here. If it's not independent, there's like a covariance between these two random variables. You cannot really separate it in this way. And this formula holds only when X, Y are independent. Okay, in our class, I think we assume X, Y is independent in the case. So we could do this. So variance of AX plus variance of BY here. Remember that for variance, we want to put the coefficient outside the parentheses when you take the square of it. So A squared of AX plus B squared VY here. Yeah, and then we're done with it. And this other just a quick example for that. I just do it 5x minus 6y, variance of 5x plus minus 6y. Of course, here x and y are independent. So we could separate them. Do you agree at this step? And then factor out, we just take the square of this number here, 525 times variance of x plus 36 times variance of y here. Just very straightforward and simple here. Then we're going to do several examples. So this case, I just write down it really fast because I think we already did enough. Just expected of 3 plus 2x is equal to expected value of 3 plus expected of 2x. This is a constant, so the expected value of a constant is just itself. And here case is just 2 times EX. This is EL. It's 3 plus 2 times EX. For variance, still we separate them. It's variance of 3 plus variance of 2x. So the variance of a constant is just 0 here. So 0 plus variance of 2x. We need to express it in variance of x in that way. So we put the 2 out and then square it. So just 4 times variance of x. For sigma L, you could remember the formula for sigma for the standard deviation. But you could also, from the variance, we got the sigma, we just take the square root of variance x, which give you 2 square root variance x, which give you 2 times sigma x. If you don't want to remember the formula for sigma x, you could just derive it from the variance. The second one is just we separate them out. Then 3 times EX hold on, is there a number in here? Okay, this is the example in page 4. And yeah, we have numbers corresponding to this example here. It's just for part A, 3 plus 2x, find the mean and the variance standard deviation of it. So we get the final step is here, 3 plus 2 times EX. EX is just the mu, it's just the mean, it's the mean of x. If we want to get the mean of the random variable L, we just plug the number inside. So in this case, EX is just 75, right? In the problem, it gave the number here. Basically, here we just set up the equations, and then because the example also gave you a number, you just plug the number inside, and you could get a final answer for that. Maybe we'll do this case in the mu for EX is just 75, EY just 50, and standard deviation of Y is just 9 here. Okay, in this case, minus 2 times EY, which gave you 3 times 75 minus 2 times 50. This will give you a final answer. It's just the final answer for this one is 125 for EW. EW is just the mean of the random variable W. So for the variance of the random variable W is no, this one. Yeah. So this is one variable 3x minus 2y, which will give you 9 times variance of x plus 4 times variance of y here. And then, we only give a sigma here, the standard deviation. In this case, give the standard deviation, we got the variance, we just take the square of the standard deviation, the sigma here, right? So we got 9 times 16 squared plus 4 times 9 squared, which give you a final answer is not in this page. And then, we got the standard deviation of this random variable W. We just take the square root of variance of W, and we are done. This one I just leave here. I mean, you could do the calculation in your calculator or manually, whatever you want here. Another one is I think basically that's all the things we're gonna cover, right? Do I cover everything? Could you check your lecture notes for Baku, like this transparency? Did I cover everything or I missed something here? .4. Did I cover everything or no? Did you check it? I know there's a last page for that, but basically this is the same thing. You talk about the variance. Did you have this page with you? Did I check yours? Mine might be different from yours. Just want to make sure I didn't miss anything.
Yeah, they have this one, but it's the same thing.
They're the same thing, right?
Yeah.
But that's why I'm a little bit confused. Just the variance, we talked about that.
Yeah.
The same thing.
And this is the first page.
Yeah, this is the previous one, right?
Yeah, I've no idea why.
Yeah, maybe that's all for today. Do you have any questions? What? Oh, I won't cover this. Baku will cover that part. The professor, instructor, she will cover that part later. Yeah, in the next class.